Welcome. Last Wednesday there was a nice talk of Maggie Miller about knotted surfaces in R4, and I wondered how does that work in the discrete. So everything can be done in the discrete. We have a notion of a manifold, for example a 4 manifold, and we have also notions of hyper surfaces or codimension 2 surfaces, and they can be constructed using this nice SAR theorem, which tells that we can just take a random map, and from a random map into a k-dimensional complex gives us a d minus k manifold. So very interesting is the case of knots, where we have a 3 manifold, a sphere 3 sphere, and then we have a codimension 2. Codimension 2 means it's just a couple of circles. It can be a knot like this, it can be a link. Actually, I wondered something I don't know. I have not found a general result about this. Is it true that every knot or every link can be realized as a level surface of, nice functions f and g, for example polynomials, and then what you want is that the f equal to 0, g equal to 0 are both nice manifolds, 2 manifolds, and then the intersection is a knot. I think it should be possible, because for knots like this it is possible. It should be also possible for links, but I've not seen a reference about this. And so in the discrete it's very nice. We can, with very little effort, we can really construct such examples, and I have a couple of examples here. I also want to mention again this fusion inequality, which is really nice, and in this context also interesting, because what we have is we have the cohomology of the space, like in a knot case this is just a circle 1 1 0, and then also the cohomology of the complement, and it's well known that the complement space determines the knot up to reflection. So the complement manifold is a manifold with boundary, and the usual thing what one does is, I have here an example of a tubular thing. What you do is you take the knot, but you don't look at the curve, you look at an open neighborhood. So what you do is you take an open tubular neighborhood, and then the complement is a closed set. So that's actually very similar to what we do here. If you look at the level, if you take, for example, 2 functions, random functions, and we look at the level curve in a 3-dimensional space, what we get is just a couple of circles. They are given as a delta set, so they are open sets. For example, here I have taken a 4 manifold, S2 cross S2. It's actually the computation which I have here on my laptop. I take a random map into K3, which is a addition complex, and then we can look at these level surfaces. And if you have one function, we get the hypersurface, which is just a 2-dimensional manifold. So very often we see, this is the cohomology of these manifolds, S2 cross S2. This is the cohomology of the 2 torus, but it's shifted because the smallest elements which we have in that construction, they are triangles. So these triangles are actually the points. That's why we have a delta set up. And then we can compute the cohomology of the complement, which is a nice, simplicial complex. It's closed. So then we have seen this inequality, and from this inequality you can get the deficit. You can see how much has been created in this case. It's actually, so the question is, what can kind of come up here? What kind of possibilities do we have? These are very small manifolds, so if you take a random function, what you get is usually level surfaces are either spheres, tori, or genus 2, genus 3 surfaces. They are not knotted in general. There's not enough space yet to be knotted. The Euler characteristic of a graph complement is always 0, because it's an oriented manifold with boundary. 3 manifold with boundary always has Euler characteristic 0 if the boundary consists of tori. And that's what we have if we have a link. For example, we can have 2 copies of a simplicial complex. We have these level surfaces, and let's assume they are the same, or isomorphic graphs, and then you can look at the isomorphism, an automorphism of the graph, and then we can glue them together along that. So I did that here. For example, this is very, very elegant in the discrete, because what we have is, and if I took a sphere, a two-sphere, actually what I took is just the icosahedron. Maybe I put the code up. So I took the icosahedron. So this has 12 points only, 12 points, and I took a function to the triangle, or two functions. This level codimension 2 just consists of 2 points. So what I wanted is this point and this point. These are two triangles which I wanted, and then what happens, these are actually kind of then two open sets. So what happens topologically when you have taken two open sets away, you could get a cylinder. So this cylinder, and you can take these two cylinders. So this is the gluing part. This is just a kind of the boundaries of these open sets, and you put them together. And it's amazing how small with how little effort you can do that. So in this case we had 12 plus 12 is 24 points, and then because of the gluing 3 points are identified, and then you have only 21 points. Of course one can get a torus also with less. We can get a torus with say 16 points if you just take the usual construction, the flat construction. This is then not flat. There are points which are have positive curvature. So in this case the torus has some points with positive curvature, some points with negative curvature. It's kind of an interesting way to construct new manifolds from old manifolds, and it's with almost no effort. The cohomology also can be computed very quickly. So in this case we have the cohomology of the complement. That's actually a sub-simplicial complex. You can just use the same code to get the cohomology of the complement. And these are all invariants of the these knotted spaces. I think that's what I actually wanted to say. Yeah, what are the possible, that's kind of an interesting question. What are the possible deficits? I have no idea what happens with the Betti numbers, which Betti numbers can really occur for the, complement of a knotted surface. Also, what happens typically? And that's kind of an interesting question, because we have a nice probability space of objects. So all the possible maps which we take, this is a finite set of maps. Sometimes it's empty, but most of the time we get the D minus K manifold. That's it for today.